My talk is handling about the meltwater-induced salinity drop in the Greenland Sea induced by that induced changes in AMOC and the onset of Heinrich-1 stadial 18,400 years ago. And all that forms a potential analog to modern trends. This work was done together with Patrick Blaser in Lausanne, you see here to the right-hand side, and most of the stable isotope data are from Antje Völker, a former graduate student of mine, and the radiocarbonates were screened by Pete Grotes in our Kiel lab. Thanks a lot anyway. To start with Heinrich-1 stadial, I need to say, what about Heinrich? What the meaning? Here you see a photography of Hartmut Heinrich when who was a graduate student at Kiel until 87, 80, something like that. And he obtained a core west of France, here the red star, and investigated the ice-rafted debris in this core and found peculiar spikes of IRD. Published that in quaternary research in those days. After some time, incidentally, Wally Broker got this paper into his hands and said, oh, let's name the spikes, or let's name the IRD spikes or Heinrich events, the events after Mr. Heinrich, and named that Heinrich event in the lab slang, he said. A synthesis on these events and cold stages was made about 15 years later by Sidney Hemming, and she found out that there's a complete Heinrich iceberg belt, the remainders of such a belt across the North Atlantic. Also, she has published that these spikes in IRD are mostly consisting of carbonate. Already Heinrich mentioned that they consist of yellowish dolomite debris, and these spikes are aligned in age, once you date them, with extreme cold spikes in the GISP-2 ice record here, as shown here in the upper part of the panel. And interestingly, they also show extreme short, extreme cold phases even in the Western Mediterranean Sea, in the Alboran Sea. So these stadials, or these climatic events, spread over the whole of Europe, also of course into the Alps, where the glaciers showed a major advance during those days, the so-called Schnitz advance. To learn more about that, now about Heinrich-1, now we are focusing on, we wonder how can we trace a Heinrich stadial in the Atlantic beyond that Heinrich iceberg belt I've shown you. It's a question, how can we find elsewhere a trace? And for this reason, we need to search for paired meltwater discharge, meltwater spikes, and we need to inspect past variations of AMOC. Damned, what is AMOC to a quaternary, a land-born geologist? So here I'd like to show you the modern Atlantic meridional overturning circulation, abbreviated as AMOC, and in a recent presentation of Freyka Williams. And this presentation is based on transect of mooring buoys here in the very northern Atlantic, and another mooring buoy array here in the subtropical event. Gradually we learned that this warm water of the so-called Gulf Stream, the North Atlantic current, doesn't go to the far north just for a reason of tourism, because it's that beautiful of Norway. No, it is due to a unique high sea surface salinity, unique in all oceans. And we wonder why is that salinity so unique high. And this is due to an East-Pacific freshwater piracy. Most of the humidity here gained by evaporation in the atmosphere is blown across the low hills of Middle America to the easternmost Pacific. As a result, salinities are about 32 per mil here in the far east of the Pacific, in contrast to very high salinities of 36, 37 here in the Caribbean and Gulf of Mexico basins. This high salinity, obviously, this is carried along with the Gulf Stream and then the North Atlantic Stream up to northern Norway. In our study, we now focus on two core sites, one here north of Iceland, PS 2642-43, and one immediately off Sarnthein or Tromsø, here in the Norwegian part of the Nordic Sea. And at least in the next slide, I'm showing you a close-up of this AMOC circulation geometry in the southern North Seas. So what is important? On one hand, we see the warm North Atlantic current, which of Norway, which is opposed to a cold Iceland-Scotland overflow of deep waters here. Also, we see that the Nordic Seas is separated from the Northern Atlantic by a sill between Greenland, Iceland, Faroe, and Scotland. Only very small passages are open, like here the Faroe Passage and the Denmark Strait. And here the core 2644 is located right near the Denmark Strait and is monitoring here this region and especially it is monitoring the Denmark Strait overflow, this dashed blue line. Also it's monitoring the Arctic waters of the East Greenland water and the warm waters of the North Iceland Erminger current. To give you an impression what's going on, I'm showing here you a model presentation of the Denmark Strait overflow, a model simulated by Kiel and others, and you see it's a dramatic flow coming between Greenland and Iceland, and it's even more dramatic once you look at the reconstruction of Wallace about 20 years ago in a north-south transect. Here he shows that the largest cataract, the largest waterfall on our Earth, with 6 million cubic meters swirl-drops falling down over 4 kilometers of water depth, down to here, this region, where this cataract then is mixing with waters of southern origin here. So it's a dramatic start of the AMOC, of the Atlantic Meridian overturning circulation here. It couldn't be more spectacular, actually, as this waterfall. What to do now? We are studying Heinrich event, Heinrich stadial 1. And for this reason, we inspect past changes in circulation geometry of the Denmark Strait overflow and in the southern Nordic seas. Second, we look into the response of the circulation geometry in the eastern Nordic seas. After all that, I tried to give you a summary of past circulation geometries in the Nordic seas. And finally, it's also important we inspect potential modern meltwater analogues we can observe today. So let's start with the changes in circulation geometry at the northwestern side of the Denmark Strait overflow. And here, once more, the position of PS 2644. It is a record right at the luff at 770 meters water depth at the luff of the Denmark Strait overflow. And perfect to watch the different currents, also to watch the East Greenland current and the North, once available, the North Iceland Irminster current. For further advance of our data, it is most important to have an accurate age control. It is simply crucial, an age control which goes far beyond conventional means of age control. What do I mean? For this purpose, at site PS 2644 versus sediment depth, we measured two extremely high resolved centennial to bicentennial resolution planktic and benthic C14 records. And they clearly show the planktic show a suite of radiocarbon plateaus, radiocarbon jumps, plateaus, jumps, and so on. And these jumps and plateaus can be objectively defined by means of the first derivative of the C14 record here, which shows this first derivative shows spikes at the jumps and such valleys at most of the plateaus. And this way, we now use the C14, the planktic C14 jumps to the whole suite of planktic C14 boundaries to tune them to a suite of atmospheric C14 plateaus at Lake Suigetsu in Japan. This record is merely based on leaves, not on any reworked plant material, and is therefore it's a pure atmospheric record, and it has been dated. The last datation was done by means of uranium thorium model ages by me here by Bronk Ramsey and co-authors 5 years ago. So here you get these ages along the plateaus one by one, and we can now tune our planktic C14 plateaus to the atmospheric and obtain on this way very precise ages of within about plus minus 50 years of those plateau boundaries of the jumps and the duration of the plateaus. And furthermore, we are happy to measure the difference of the average age of each plateau, say 2A here, with the atmospheric plateau and obtain a difference of 1890 years, or here of plateau whatever 4 to plateau 4 at Suigetsu. And on this way we obtain a new tracer of oceanography that is here assigned in blue numbers, here say 1890 years and so on, up to 2,200 years here during earlier times, which belong to the LGM. Yeah, so we get a clear feeling of the variation of surface water reservoir ages, are called marine reservoir ages also, all based on this planktic foraminiferous pachyderma left. Yeah, and likewise, you also can obtain the ventilation ages of deep water. These green blood dots here, they represent the benthic ages, and you will wonder, oh dear me, they are younger than the planktic ages. Yes, that is true. The paired benthic ages at this location are underflown by youngish waters for reasons we did not discuss yet. So based on that, then after all, we get planktic and benthic reservoir ages. We also get an absolute age within plus minus 50 years of all major events. Based on this chronology here, you see the chronology now plotted, we are now showing the delta O18 values of planktic neogloboquadrina pachyderma left, and these are the red dots here, all over the last glacial maximum. Here they are equally low, perhaps here a little rise, and they are at the extreme of the whole ocean, the highest values we find over the whole ocean. And suddenly, most suddenly, at 18,400 years ago, they suddenly rise. There can't be such a temperature rise during that time, 18,400 years in the Nordic seas. So we must explain that as a record of meltwater discharge over altogether here 1,400 years or 1,200 years up to here. Very interesting to find this onset of meltwater discharge precisely coeval here with a major change in the North Grip ice core, North Grip ice core record. You see that precisely the same age, and shows that here this introduction of meltwater north of Iceland, or northwest of Iceland, was aligned with a major climatic change. So we now define this as Heinrich stadial 1b, or the start of Heinrich-1 as a whole here over this time. It's also interesting to see what where the meltwater may have come off. For this reason, we have 25 years ago we mapped this low in the low in delta O18 values and found here a tongue of meltwater enriched waters that obviously came from somewhere south of Greenland, and by now we don't know yet precisely where this meltwater has come from. That this has to be done. There's a different meltwater mass in the east, and I'll refer to that later on. Also very interesting is the distribution of benthic O18 values, delta O18 values, here measured for single tests of benthic foraminifer. This guy here, and each sample shows a broad array of values. Obviously, an interannual or seasonal change of values, but the maximum values here at about 4.5 or 4.45. Here, they suddenly end here at 18,400 years, and right at with the start of the meltwater import, they suddenly rise by a difference equivalent to 3.5 centigrades up to this level. And so we see that Denmark Strait overflow suddenly has warmed up dramatically for a deep water flow in the Nordic Seas, 3.5 centigrades. That's a high difference indeed. So we wonder, what does the ventilation do? And for this purpose, we also have based on single specimens. We measured the epibenthic C13 value on single specimens, and they are extremely high during the LGM times until about 18,200 years ago. And then these extremes disappear, and also here these low values these occasionally are replaced by a cloud here, a population of much lower delta C13 values, a drop in ventilation after about 200 years after this change, 18,400 years. Let's continue. Here we plot the reservoir ages of blue of surface water, red of bottom water, and during the LGM, it's very obvious that here the planktic were a little higher, the planktic reservoir ages were a little higher than later on, but basically it was not that much different. It's always the same East Greenland current which carries along these values. However, the benthic, the bottom water ventilation ages, they start to drop here near 90,000 dramatically. In the beginning, we didn't believe in one of these dates here, and so we measured the second one, but the first one was simply confirmed. And then after this time, after 9, the values rise again to the age of the more or less the glacial age, but after 18,200, after that, the benthic ventilation age go to they vary about near 1,200, 1,400 years. Here, occasionally they drop down to less, to about 800 years, 700, 800 years. So it's a completely different age of bottom waters as compared to the LGM bottom water we need to keep in mind. What does that really mean? For this purpose, I'm now showing the differential origin of Denmark Strait overflow waters today, as compiled by Vogi and others here for this transect. And here he measured a core of Denmark Strait overflow water with extremely high with contours of potential density, a maximum more than 28.05. Yeah, and this core is then assigned to Arctic deep waters. That these Arctic deep waters, they arrive from the Arctic Ocean today, and they are overlain by a slightly less dense water masses that is contributed by the North Iceland Jet. And here I show you an additional source of Denmark Strait overflow water, NIG, the North Iceland Jet. And this North Iceland Jet obviously contains less dense waters than the Arctic waters. How can we distinguish that over the past? For this reason, Patrick Blaser has measured the neodymium isotopes, radiogenic traces, the neodymium isotopes, and the lead 206, 204 trace ratio, and they show here, especially the lead isotopes, a major drop here, which is characteristic of basaltic sediments, which are eroded. And the same, this is matching a clear rise of neodymium isotopes, and both of them suggest that the Denmark Strait overflow, the source waters of Denmark Strait overflow, must have passed basaltic sediments of the Iceland-Scotland ridge to get here this basaltic signature. Altogether, they also show a tremendous rise in the sedimentation rate. Summarizing all that, we need to conclude that during Heinrich-1, the Denmark Strait overflow waters didn't contain anymore this extremely dense core of any Arctic deep waters. These Arctic deep waters were replaced by waters of the North Iceland jet, of this current here. And the North Iceland jet obviously has passed the basaltic sediments here of the Iceland Faroe Ridge here, and has included waters of the upper North Atlantic Intermediate, waters. These waters are characterized by they reveal a rise in bottom water temperature. They are far warmer than the cold waters coming today from the Arctic, and they have shown a drop in bottom water ventilation, as shown you on the previous slide. So interesting, we see a major change in the waters feeding the Denmark Strait overflow. It continued to flow, but it was weaker and contained different source waters as compared to the LGM, as compared to today. Next, we are now looking into the response of circulation geometry in eastern Nordic seas. Here, since 18.4 calendar years, mark a major tipping point of AMOC. And for this purpose, now we turn our attention here to this core 23074, which is monitoring the North Atlantic jet and the Iceland-Scotland overflow water. Like in the previous core, we need a highly precise, highly accurate age control. And this accurate control we achieved by, once more, by a high-resolution Planktic C14 record, the red dots here, and also we measured benthic ages. They are younger, partly a little higher than the Planktic ones, but in general they are the same, and we have to think about their origin. And to derive the calendar ages we are looking for, the suite of Planktic boundary ages is now tuned to the suite of atmospheric plateaus plotted down here, which is age calibrated by Bronk-Ramsey. And as with the other core, we gain a new tracer on this way, the Planktic reservoir ages. These blue numbers here, the very highly variable. Here they are 600 years, 800 years, 500 years, and here they rise to 1100, 12, and 17, 2000 years, and suddenly drop back to about 300 years. So you see, reservoir ages Planktic are highly variable, and based on paired Planktic and benthic values, age values, we can also get the benthic ventilation ages. On this base, we now plot once more our delta 18 record of plankton as compared to the North Cape record, and you'll be disappointed. There is no meltwater signal at 18,400 years. No, not ever. But yeah, we can see that at this time, here 18,400, we get a major rise in both, in the planktic ages, the blue record, here the blue record, and then even more so in the benthic record. Here the benthic records obviously are a little higher than the local planktic records. And so we conclude that during the LGM, most of the benthic of the deep water was due to convection, was induced by local convection somewhere in the Nordic seas. And during Heinrich-1b, they were induced by some local brine water formation. And later on, we return back to convection-based, convection-induced deep water formation. So dramatic changes over time in the Nordic seas, key points of global change. So to summarize that, events of Norway after 1,400 years, they show a high rise in surface water closely assembled to the age of East Greenland current waters. The ages, just to give you here, these ages, the planktic ages we just had shown here, they are precisely the same ages we found in the East Greenland current in the other core. That reflects a major AMOC tipping point. So Arctic surface waters, instead of North Atlantic current, Arctic surface waters extended up to the west of Norway after this time. And these cold waters induced a perennial sea ice cover. And this was, of course, caused a major change. This perennial sea ice cover led to an immediate cooling during Heinrich State 1b over the whole northern atmosphere up to the Indian Ocean, a major change. I don't like to conceal that there's a second meltwater event here, this one, at this site 230464, a second meltwater event that also was coeval with a cooling here on North Cape, a major cooling, and the meltwaters, while mapping it and dating them, they come from a breakdown of the Barents Sea ice shelf, or a breakdown of the saddle ice between Spitsbergen and northern Norway. This is a separate story I won't extend now because time is limited. Let's continue. Yeah, we see that this second event led to a major breakdown of surface water reservoir ages, of planktic ages, and of benthic ones, the red curve. And this breakdown is also confirmed by coral-based uranium thorium ages. So we are well sure about this change. And with the beginning of the Bølling-Allerød time here, we have a very young waters, and all the deep water are convection induced, whereas previous time prior to that, brine water induced waters formed the deep water. To continue, I like to show you something I'm actually not allowed to show, never show in a talk, a table I learned, yeah. But sometimes the match is so fascinating that I have got to show that. We here have listed a number of events and major features, like the weather age layer, the abrupt delta-18 drop due to meltwater outbreak and so on. And what we see is here that the ages, the C14 ages, converted by means of plateau tuning technique, which I've shown you, they with a variable marine reservoir ages, they completely fit to the incremental age scale of events found on Greenland, both in GISP2 and North Grip Island. You see several cases here, where they fit precisely, whereas the conventional way to imply Incal 20 ages, yeah, and with a reservoir age of 400 years, many authors use, we arrive at ages which are fairly different, up to 2,000 years long, larger or higher, and so on. Also, the firmer way to create calendar ages by Antje Völker by means of tuning to GISP2 has led to fairly different ages, different from the GISP2 and North Grip ages we now know of. So with this at hand, I'm now showing you, I'm now giving you a summary of past circulation geometries in Nordic seas. And here we go to the site north of Iceland, PS26. This is the sill between Nordic seas and North Atlantic. And this is our site. Here we see the LGM. During the LGM, surface water ages were 1900 to 2200 years, bottom water 24,000, and the perennial sea ice cover, like as today, has marked this site. And the Denmark Strait overflow was fed by very old Arctic water, deep waters. If we compare that to the Heinrich-1, we see that the bottom water ages have become much younger. You see that? The surface water were more or less the same, 1900 to 202, and here, of course, they became a little younger here, but the bottom water ages are really different. And from this, we conclude also on the basis of bottom water temperature and bottom water ventilation, that the NIJ, the North Iceland jet, in those days also has accumulated water of North Atlantic intermediate water, topmost North Atlantic intermediate waters. They were less ventilated, youngish, as to be expected. So this is a major change of two systems, a tipping point, we may say. In the east of Norway, the LGM shows the incursion of warm North Atlantic current with youngish water, 500 to 700 years, sometimes up to 1100 years, and the convected deep waters here at 1200 meters water depth approximately, they are likewise young, fairly young. And the next, of course, will show you the Heinrich-1 stadial. Here, after the tipping point of 18,400 years ago, old, that means cold, Arctic surface water have reached Norway. Here, these waters you can have with an age of 1900 to 2100 years as compared to these youngish ages. Accordingly, also here, the local brine waters which were formed below that perennial sea ice cover, which induced Heinrich-1, very important. The perennial sea ice of Norway has a dramatic effect on the whole northern hemisphere. These brine waters also have fed a weak overflow here to the North Atlantic, here feeding southern source waters, as Dan Thornley has shown. So far, now it's finally time to show the potential modern meltwater analog to the onset of stadial 1. And here I like to refer to this figure where we found this incursion of of meltwaters, fresh waters from the North Atlantic into the westernmost Nordic seas. And today it's interesting, we have a very strong melt of the ice of the Greenland ice sheet. We see huge current streams of meltwater here. Just for comparison, look at these little boats here on top. Yeah, it's immense meltwater masses. And Smith has shown that that the ice has much enlarged ice crevasses, enormously so, as characteristic for a breakup of ice sheets. This breakup is Chudley has recently shown. Chudley, he just compared 2016 to 2021 here, and you see that here a little Nunatak was that small. After 5 years, it was that large. Or this ice-covered Nunatak became that bare of any ice, and so on. Or here, the tongue region of these glaciers has much compared as to there. So all this is not new to this. He calculated the water masses available over the 5 years and got a major discharge here from the center of Greenland. All that is, of course, related to the modern global warming we all know of, or only some extreme climate skepticists don't believe in that. Here, this warming of the troposphere, and this main warming, however, has a hole. Here, this blue spot here, it shows that the warming is aligned to a cooling trend just right now of Greenland, a fingerprint of a reduced AMOC, dramatic. And we can also see the same result by comparing records here of global marine temperature and the local sea surface temperature anomaly in the subpolar gyre here. And of course, everybody is curious and wondering, can't we extrapolate that? Can't we extrapolate here down that? It's not that easy, I would say. We have to consider here the Ramsdorff model, the Ramsdorff results on bifurcation puddles. If you increase the freshwater flux, all models, about 12 models, show that there's a bifurcation point here, a sudden bifurcation point, and then there's a point of no return or late return. And if we sum up all these points and add them to our extrapolation, we shall arrive here at a breakdown of AMOC in the Nordic seas at near 2060. Very exciting, I think, as Ditlevsen have shown recently. After all that, I'd like to sum up. The take-home message is we found a close-mate match of calendar ages based on radiocarbon plateau tuning as compared to the incremental age scale of North Stream, a match within 50 to 100 years. Next is that after 18,400, we see an onset of glacial meltwater injection north of Iceland, and they led to a major change in the source of Denmark Strait overflow. They mean a climate tipping point indeed, with an abrupt warming, drop in ventilation age of the Denmark Strait overflow. And instead of Arctic waters, we see now the North Iceland Gem forming a major source of Denmark Strait overflow. And all that led to a coeval onset of cold Heinrich stage 1b. East of Norway, however, we have seen a major rise in planktic and benthic ventilation ages over that time, and a warm North Atlantic current today, very important to all Norwegians and their apple trees, was replaced by old cold waters and perennial sea ice. The LGM deep water ventilation was replaced by weak brine water formation, and finally, changes in the circulation temperature of AMOC, the ocean CO2 caused the ocean release of CO2, and that in turn a minor radiocarbon plateau 4A. We didn't have time yet to discuss, but any other interesting result. And after all that, I'm asked, I can show you that I tried to show you that the start of Heinrich-1 may serve as a metaphor for modern meltwater-induced AMOC evaluation. Really a fantastic metaphor to understand what we are going to have in 35 years approximately. And now thank you for your long patience, and hopefully most of them, like here, those you will start to be awake. Thank you a lot.
Thank you very much, Michael. That was masterful. Very interesting. I will start off the questions with the University of Bergen.